Most of the universe is not made out of atoms. Every textbook is wrong. Every chemistry class is wrong. Your high school chemistry teacher was wrong in saying that everything's made out of atoms.
Did you know that a groundbreaking discovery has just turned our understanding of protons on its head? Scientists have found evidence of an elusive particle inside protons that defies explanation and may force us to rewrite physics textbooks.
Planck mass is a numerical number in the units of mass that naturally emerges by a particular combination of Planck's constant, the gravitational constant, speed of light. You put them together in the right configuration and you get something with the units of a mass. And the particular amount of mass is about 10 to the 19 times the mass of the proton. 10 to the 19. That's huge, right? So the fundamental mass scale that seems to emerge from our description of the forces of nature and quantum mechanics, speed of light, gravity, and so forth, that number is 10 billion times larger than the scale of masses that we actually see in the particles in the world around us. So the question is, why is there such a broad spread of scales? And we've been trying to come to grips with that problem for a very long time. The idea of supersymmetry, this idea that for every known particle, there's a partner particle whose quantum mechanical spin would be different in slightly technical language. That idea was partly introduced to deal with this hierarchy problem. The quality of those partner particles within the theoretical framework allows for a very natural explanation for why the particles would have such a low mass. It all comes down to a symmetry principle. Whenever a number is really small, a natural explanation is, well, it must be small because some kind of symmetry keeps it small. I mean, 0 is the most symmetric number we know. You multiply it by anything, you divide it by anything, it stays the same. Symmetry is a quality of a system that is unchanged under a whole variety of transformations, right? You take a sphere, you rotate it. If it's a nice silver sphere without anything printed on the surface, no matter what angle you look at that sphere, no matter how you twist it and turn it, the sphere looks the same. It is highly symmetric. Similarly, the number 0 is highly symmetric. As I said, you multiply, divide, doesn't change. So if you can find a symmetry that naturally yields 0 mass for the particles, then you say to yourself, well, maybe that's why they're so small. And maybe that symmetry is not exact. Maybe that symmetry is almost, but not quite an exact quality of the world, the environment. And that would allow the masses to be near 0, but not exactly 0. And this is this approach that supersymmetry gives us. So the problem, of course, is no one's found the supersymmetric particles. Large Hadron Collider, the hope was that it would find all sorts of other particles that we hadn't previously seen. Partners of the electron called the supersymmetric electron or the selectron. Partners of the quarks. Squarks would be the supersymmetric partners of the quarks. So it sounds a little silly, but this is a real mathematical theory. And look, a $10 billion machine was built in part to try to find these supersymmetric particles.
Imagine a new component hidden within the very building blocks of matter. This revelation could change everything we thought we knew about the universe. Stay tuned, because we're diving deep into this astonishing discovery that challenges the fundamental laws of physics and could revolutionize science as we know it.
What is quark-gluon plasma?
Yeah, so that's shortly after the billionth of a second after the Big Bang. So
Yeah.
you end up with a soup of quarks and gluons. So quarks are the building blocks of protons and neutrons, and gluons are the things that stick them together. So a proton has 2 up quarks and a down quark, and a neutron has 2 down quarks and an up quark, and so on. So they're the constituents, the protons and neutrons, which are the constituents of our atomic nuclei. So if you go to very high temperatures or high energies, then the protons and neutrons fall to bits. Then you end up with a soup of quarks and gluons, and that's the quark-gluon plasma.
And it's insanely dense, right?
Yeah, well, very high energy. So you get that. So we've been exploring that because we don't only collide protons together. We can collide lead nuclei together or silver nuclei together at the LHC, and that's when you make these kind of soups of nuclear matter.
Particle physics is a branch of physics that studies the fundamental particles of the universe and the forces through which they interact. It seeks to understand the basic building blocks of matter and the underlying principles that govern their interactions. This field has given us profound insights into the nature of the universe, from the smallest particles to the vastness of the cosmos. To explore these particles, scientists use particle accelerators, which are complex machines designed to accelerate charged particles, such as protons or electrons, to very high speeds and then collide them. These collisions create conditions similar to those just after the Big Bang, allowing scientists to study the resulting showers of subatomic particles. The Large Hadron Collider, or LHC, at CERN is the most well-known particle accelerator, but there are many others around the world, each contributing to our understanding of particle physics. Particle accelerators work on the principle of accelerating particles using electromagnetic fields. These particles are guided around a circular or linear track by magnets, gaining energy with each pass. When they reach the desired speed, they're made to collide with a target or with each other. The collision produces a burst of energy that creates new particles, which can then be detected and analyzed. One of the key goals of particle physics is to understand the fundamental particles that make up matter. For a long time, it was believed that atoms were the smallest units of matter. However, further research revealed that atoms are composed of protons, neutrons, and electrons. Protons and neutrons, in turn, are made up of even smaller particles called quarks, held together by particles known as gluons. Studying these particles requires sophisticated equipment and techniques. Particle accelerators are equipped with detectors that can track the trajectories of particles, measure their energy and momentum, and identify their type. The data collected from these experiments is analyzed to understand the properties and behavior of the particles. The discovery of new particles and the study of their interactions provide insights into the fundamental laws of physics. For example, the discovery of the Higgs boson at the LHC confirmed the existence of the Higgs field, which gives particles their mass. Similarly, the discovery of the charm quark in protons, as discussed in this article, has significant implications for our understanding of the structure of matter. Particle physics is a highly collaborative field, with scientists from around the world working together on experiments and sharing data. This collaboration is essential, given the complexity and the scale of the experiments. The results of these experiments not only enhance our understanding of the universe, but also have practical applications, such as in medical imaging and cancer treatment. Protons and neutrons are the building blocks of atomic nuclei, and understanding their structure is crucial for understanding matter itself. These particles are composed of even smaller particles known as quarks, which are held together by gluons. This section delves into the intricate structure of protons and neutrons, focusing on the roles of quarks and gluons. Quarks are elementary particles that come in 6 different types, or flavors: up, down, charm, strange, top, and bottom. Protons and neutrons are primarily made up of up and down quarks. A proton consists of 2 up quarks and 1 down quark, while a neutron is made up of 2 down quarks and 1 up quark. These quarks are held together by gluons, which are the carriers of the strong nuclear force, one of the 4 fundamental forces of nature. Gluons are massless particles that act like the glue holding quarks together within protons and neutrons. They're constantly exchanged between quarks, creating a strong force field that binds the quarks together. This force is incredibly strong, far stronger than the electromagnetic force that holds electrons in orbit around the nucleus. The energy associated with gluons contributes significantly to the mass of protons and neutrons. The behavior of quarks and gluons is governed by the principles of quantum chromodynamics, or QCD, a theory that describes the interactions of these particles. QCD is a complex and highly mathematical framework that explains how quarks and gluons interact, and how they form composite particles like protons and neutrons. One of the key features of QCD is color charge, a property analogous to electric charge in electromagnetism, but with 3 types instead of 2: red, green, and blue. Quarks carry these color charges, and gluons act to neutralize them, ensuring the particles like protons and neutrons are color neutral. The internal structure of protons and neutrons is not static. Quarks and gluons are in constant motion, interacting with each other in a dynamic and complex manner. This internal motion contributes to the overall properties of the particles, such as their mass and spin. The exact distribution of quarks and gluons inside protons and neutrons is still a subject of active research, with experiments continually refining our understanding of these particles. Visualizing the internal structure of protons and neutrons is challenging due to the tiny scales involved. However, advanced computational simulations and experimental data from particle accelerators have provided us with increasingly detailed pictures. These simulations showed that the distribution of quarks and gluons inside protons and neutrons is not uniform. Instead, it's a seething, dynamic environment where quarks and gluons are constantly interacting and exchanging energy. Recent advancements have allowed scientists to visualize protons with unprecedented detail. For example, simulations from the Jefferson Lab have shown that protons contain dense clouds of gluons, which account for most of the proton's mass. These simulations provide insights into the distribution of quarks and gluons and how they contribute to the proton's overall structure. The recent discovery of the charm quark in protons represents a significant milestone in particle physics, challenging our existing understanding of the structure of protons. This section explores the details of this discovery, its experimental basis, and its implications for our knowledge on fundamental particles. Protons were traditionally understood to be composed of 3 quarks, 2 up quarks and 1 down quark. These quarks are bound together by gluons, which mediate the strong nuclear force. This model has been supported by numerous experiments and has formed the basis of our understanding of nuclear physics. However, recent experiments have suggested that this picture might be incomplete. The charm quark is one of the 6 flavors of quarks, heavier than the up and down quarks that make up protons and neutrons. It was first hypothesized in the 1970s and later discovered in experiments involving high-energy particle collisions. The existence of charm quarks within protons, however, was not anticipated in the traditional 3-quark model. The discovery of the charm quark within protons came from the analysis of data from high-energy particle collisions conducted at various particle accelerators around the world. These experiments involve accelerating protons to near light speeds and smashing them into each other, creating conditions that allow scientists to probe the internal structure of the protons. Detectors surrounding the collision points capture the resulting showers of particles, which are then analyzed to identify the particles produced in the collisions. Researchers employed advanced statistical techniques and machine learning algorithms to analyze the vast amounts of data generated by these collisions. Machine learning models were used to identify patterns and discrepancies that might indicate the presence of charm quarks within protons. These models were trained on theoretical predictions and experimental data, allowing them to make highly accurate predictions about the behavior of particles in the collisions. The discovery of charm quarks within protons has far-reaching implications for particle physics, reshaping our understanding of fundamental particles and their interactions. This section explores the theoretical, experimental, and practical implications of this groundbreaking finding. Theoretically, the presence of charm quarks in protons challenges the conventional quark model, which posits that protons are composed of 2 up quarks and 1 down quark. This discovery suggests that protons may contain additional quark flavors, leading to a more complex internal structure. The inclusion of charm quarks in protons aligns with the concept of C-quarks, which are quark-antiquark pairs that transiently appear within protons and neutrons. The presence of charm quarks in the C-quark population indicates a richer and more dynamic internal structure than previously thought. This discovery also has significant implications for our understanding of quantum chromodynamics, or QCD, the theory that describes the interactions of quarks and gluons. QCD is a cornerstone of the standard model of particle physics, and any new findings related to quark behavior and interactions provide valuable insights into this theory. The presence of charm quarks within protons may lead to revisions of the QCD calculations and model, improving our understanding of the strong nuclear force and the behavior of quarks and gluons. Experimentally, the discovery of charm quarks in protons underscores the importance of high-energy particle collisions in exploring the fundamental structure of matter. These experiments provide the conditions necessary to probe the internal structure of protons and neutrons, revealing new and unexpected features. The use of advanced data analysis techniques, such as machine learning, has been crucial in identifying the presence of charm quarks, highlighting the importance of these methods in modern particle physics research. The implications of this discovery extend beyond theoretical and experimental physics. It may also impact our understanding of nuclear reactions and processes, such as those that occur in stars and nuclear reactors. The behavior of protons and neutrons, and their interactions with other particles are fundamental to these processes. A more accurate understanding of the internal structure of protons and neutrons could lead to new insights into the mechanisms underlying nuclear reactions and the behavior of matter under extreme conditions. Machine learning has become an increasingly important tool in particle physics, enabling researchers to analyze vast amounts of data and identify subtle patterns that are otherwise difficult to detect. This section explores the role of machine learning in the discovery of charm quarks within protons and its broader applications in particle physics. Particle physics experiments, such as those conducted at the Large Hadron Collider and other particle accelerators, generate enormous amounts of data. Each collision produces a shower of subatomic particles, which are then detected and recorded by sophisticated detectors. Analyzing this data to identify interesting events and new particles is a complex and time-consuming task. Traditional data analysis methods are often insufficient to handle the sheer volume and complexity of the data. Machine learning, a subset of artificial intelligence, offers powerful tools for analyzing large and complex data sets. Machine learning algorithms can be trained to recognize patterns and make predictions based on large amounts of data. In particle physics, these algorithms can be used to sift through collision data, identify interesting events, and make precise measurements of particle properties. In the case of the discovery of charm quarks within protons, machine learning played a crucial role. Researchers used machine learning models to analyze data from thousands of high-energy particle collisions. These models were trained on theoretical predictions and experimental data, allowing them to identify subtle discrepancies that might indicate the presence of charm quarks. The use of machine learning enabled researchers to achieve a level of precision and accuracy that would be impossible without traditional methods. One of the key advantages of machine learning in particle physics is its ability to handle high-dimensional data. Particle collisions produce data with many variables, including the trajectories, energies, and momenta of particles. Machine learning algorithms can process this high-dimensional data and identify patterns that are not apparent in lower-dimensional projections. This capability is particularly important for identifying rare events and new particles that produce only subtle signals in the data. Machine learning also helps to reduce biases in data analysis. Traditional data analysis methods often rely on predefined criteria and assumptions, which can introduce biases and limit the discovery of unexpected phenomena. Machine learning algorithms, on the other hand, can be trained to explore a wide range of possibilities and make predictions based on the data itself, rather than predefined assumptions. This flexibility allows for the discovery of new and unexpected patterns in the data. The use of machine learning in particle physics is not limited to data analysis. It also plays a role in detector design, optimization, and calibration. Machine learning algorithms can be used to optimize the performance of detectors, ensuring that they're sensitive to the signals of interest and minimizing background noise. These algorithms can also be used to calibrate detectors, improving the accuracy and reliability of the measurements. The discovery of charm quarks within protons opens up some new avenues for research and has the potential to impact various scientific and technological fields. This section explores the future directions for research in particle physics and the potential applications of this discovery. One of the primary future directions for research is to further investigate the presence and behavior of charm quarks within protons. This involves conducting more high-energy particle collision experiments and using advanced data analysis techniques to confirm and refine the findings. Researchers will aim to quantify the proportion of charm quarks within protons, understand their distribution, and explore how they interact with other quarks and gluons. This research will provide a more detailed and accurate picture of the internal structure of protons. Another important area of research is to explore the implications of charm quarks for quantum chromodynamics and the standard model of particle physics. The presence of charm quarks within protons suggests that our current understanding of QCD may be incomplete. Researchers will work on developing new theoretical models and refining existing ones to incorporate the presence of charm quarks and other potential quark flavors within protons. This research will deepen our understanding of the strong nuclear force and the behavior of quarks and gluons. The discovery of charm quarks within protons also has implications for the study of exotic matter and particles. Researchers will investigate the conditions under which charm quarks and other exotic quarks can form stable particles. This research may involve exploring the behavior of quarks and gluons under extreme conditions, such as those found in the early universe or within neutron stars. Understanding the formation and stability of exotic matter could lead to new insights into the fundamental nature of matter and the universe. In addition to theoretical and experimental research, the discovery of charm quarks within protons may have practical applications in various fields. For example, a deeper understanding of the behavior of fundamental particles could lead to advancements in material science. Researchers could develop new materials with novel properties by manipulating the interactions of fundamental particles. These materials could have applications in a wide range of industries, from electronics to aerospace. In the field of medicine, the knowledge gained from particle physics research can be applied to improve diagnostic and therapeutic techniques. For instance, particle accelerators are already used in cancer treatment through techniques such as proton therapy, which targets tumors with high precision while minimizing damage to surrounding healthy tissue. A better understanding of proton structure and behavior could enhance these treatments, making them more effective and accessible. The discovery of charm quarks within protons also has implications for technology and computing. The advanced data analysis techniques used in particle physics, particularly machine learning and artificial intelligence, can be applied to other fields that require the processing and analysis of large data sets. These techniques can improve the efficiency and accuracy of data analysis in various domains, from climate modeling to financial forecasting. In addition to the practical applications, the discovery of charm quarks within protons contributes to our fundamental understanding of the universe. Particle physics seeks to answer some of the most profound questions about the nature of matter and the forces that govern the cosmos. Each new discovery brings us closer to a more complete understanding of the universe's origins, structure, and evolution. This knowledge enriches our scientific and philosophical perspectives, fostering a deeper appreciation for the complexity and beauty of the natural world. Future research in particle physics will also focus on exploring the potential connections between different forces in particles. For example, researchers are investigating the possibility of a unified theory that can describe all fundamental forces in particles within a single framework. The discovery of new particles and interactions, such as the charm quarks within protons, provides crucial clues that can guide this quest for a unified theory. Another exciting direction for future research is the study of dark matter and dark energy, which are believed to make up most of the universe's mass and energy. Understanding the behavior and interactions of fundamental particles, including quarks and gluons, could provide insights into the nature of dark matter and dark energy. This research has the potential to revolutionize our understanding of the universe and address some of the most pressing mysteries in modern physics. Collaboration and international partnerships will continue to play a vital role in advancing particle physics research. Large-scale experiments, such as those conducted at the LHC and other particle accelerators, require significant resources and expertise from scientists around the world. By working together, researchers can share data, develop new technologies, and make some groundbreaking discoveries that push the boundaries of our knowledge. So thanks for watching this video. We hope you enjoyed it. If so, please give this video a thumbs up and subscribe for more videos like this.